All right, greetings. Thank you all for attending this webinar, which is hosted by the Center for Advanced Transportation Mobility. I am Dr. Miranda McBride, the director of the Center for Advanced Transportation Mobility, which is a Tier 1 university transportation center funded by the U.S. Department of Transportation under the FAST Act. Today's webinar is being presented by Dr. Venktesh Pandey. Dr. Pandey is an assistant professor in the Department of Civil, Architectural, and Environmental Engineering at North Carolina Agricultural and Technical State University. His research integrates intelligent transportation systems in emerging mobility services in traffic operations, congestion pricing, and transportation planning models with a focus on sustainability. Dr. Pandey received his PhD in civil engineering from the University of Texas at Austin in 2020, where his research focused on modeling efforts for understanding and improving our transportation systems under traffic dynamics and stochasticity. Dr. Pandey also has broad interest in improving the engineering education systems of the future. He currently serves as a co-PI on a National Science Foundation funded project that establishes a transportation digital badge program for effective engagement of undergraduate students at North Carolina A&T in transportation education and careers. In this webinar titled Modeling Approaches for Equitable Dynamic Congestion Pricing, Dr. Pandey will present his UTC-funded research, which focuses on investigating equity issues of express lane dynamic pricing. Dr. Pandey, the floor is yours.
Okay, I just unmuted myself. Thank you, Dr. McBride, for introducing me, and thanks everyone for joining us for the webinar today. So as Dr. McBride said, I'll be talking to you all about some of the research that we have been doing over the last year on taking some modeling approaches towards creating more equitable congestion pricing for express lane facilities. And as mentioned, I want to acknowledge the support of the Center for Advanced Transportation Mobility for funding this research, and I want to acknowledge the role that all the students have played as part of the work that I'll be presenting. So some of the research is still kind of ongoing as part of the process, but I hope to give you like a good enough insight into the motivation and some of the preliminary results, so that way we can have more open-ended discussion about the questions related with the dynamic congestion pricing. With that said, I plan to talk around for like 40 or so minutes, so hopefully I'll keep the timing in check. My presentation, I'll start with a background of like what this congestion pricing issue is, and the focus that I'm trying to bring, which is the modeling focus. Then I'll talk more about the planning models, like what is the methodology used to integrate equity as part of those, and look at some of the findings and ongoing work there, and looking at the day-to-day operation models next, where we again look at methodology and ongoing work. Okay, so I guess we all are aware about some of the commonly known congestion pricing techniques which are used to mitigate traffic congestion. So broadly, the philosophy of congestion pricing is there is a lot of demand for people willing to travel from one place to the other, and in some ways we want to internalize the burden that each individual poses through congestion on other travelers. So the philosophy of pricing is to internalize this externality. So if you look at it in terms of economics terms, it's the terminology, and it's implemented through different mechanisms such as cordon pricing, dynamic toll rates, express lanes, and many countries across the world have implemented different forms of each of these and have had successes with different ones of them. So they have been around for a long time, and in many ways they serve the very much needed purpose of mitigating congestion, as well as providing us with sufficient funds in many cases. Because as we also know that, especially in the United States, the impact of gas tax revenue has been declining over the last few decades. So in some ways, these congestion pricing methods kind of support the transportation agencies by providing sufficient funds. So now let's talk about the concept of equity. if we root ourselves in the sort of the literature on social justice, broadly, the goal of equitable transportation service is to make sure that we are providing equal levels of access to affordable and reliable options for all across all population groups. Again, which is based on the needs of the population that we are serving. So like the bottom line definition is making sure that everyone has equal level of access to transportation facilities. So when we talk about transportation systems, there are several decisions where these like equity can play a big role. For example, whenever we are providing transportation facilities or services, then we can think about who will access them and whether the access is equitable or not. So for example, provision of sidewalk or ramps for people with disabilities is one example. Fees and regulations is another example where and congestion pricing falls under them, and where we consider what is the impact of different type of methods related to congestion pricing, parking fees, etc., on different groups of users. And when we talk about accessibility across population groups, here we talk about like more of a spatial as well as geographical accessibility. So looking at like different neighborhoods, what is the quality and frequency of transit service? That's one example. And lastly, like decisions around compensation for these externalities. Also incorporated. For example, like if we know that there is a highway which passes through, passes near a neighborhood and creates excessive noise pollution, then we can sort of compensate those people in those neighborhoods or displace them so that to account for more justified way of, I mean, even though there is like a lot of debates around it, but like what I want to say is like, in some ways we want to compensate for like, if we create any transportation project, the burden that we might pose on other people, we might want to compensate groups for those. So broadly, in my
All right, Dr. Pandey, we have lost your audio, at least I have.
I have too.
Me, yes, we cannot hear it.
Okay, let's give him a second. It might have been a connectivity issue.
And his picture was freezing before that.
Yeah, it looks like we lost his PowerPoint, so he's probably trying to log back in. So if everyone just
I'm
there
really
you
sorry.
Okay,
Now
yeah.
you're back.
Okay, when did I lose call? I didn't realize. Was it right? I don't know what happened exactly.
It's only been about a minute. So
Okay.
yeah.
So then I think I can just hop back on the slide and start presenting. Okay, can you all see the screen?
Yes.
Okay, perfect. Sorry about that technical issue.
Not a problem.
So yeah, as I was saying, congestion, the focus that I'm trying to bring in is through express lane facilities, which have been sort of an emerging tool across the United States to provide travelers a reliable travel time. So these are the lanes which run in parallel to regular lanes and where you pay a toll, which changes with time. And in some ways, this is always a congestion-free lane. So we provide reliable travel time, and we can sort of exploit travelers' willingness to pay revenue, much needed revenue for infrastructure projects. So there are the growth of express lanes across the United States has been exponential over the last few years. There are more than 60 operational express lanes, and the plan for the current express lanes under construction, I think it will go above 100 this year for sure. So I think the key question that we want to investigate is that do these facilities leave the economically disadvantaged travelers worse off in some ways, or in some ways like identifying are there sort of equity barriers for accessing these facilities. So if you look at some of the real world case studies around the express lanes, we see that there are different factors that impact like access to express lanes. So it's not very black and white that high income people will benefit and low income won't. There is a good sort of trade-off across like income range, residential location, and urgency of travel, which impacts the usage of those lanes. And express lanes, because they offer a choice to pay a toll or not pay a toll, in some ways they are argued that they are more equitable than a standard toll road, because there is an option for people to, if they don't feel for paying it, they are not sort of blocked from traveling in some ways. However, the issue is like usually the general purpose lanes are a little bit more congested. So I guess the issue still pertains like, are we leaving certain groups of travelers towards lanes which are usually more congested? There have been several studies recently, and for I-405 lanes, actually it was found that low income households can actually benefit a little bit through these express lanes, because there is more frequent period, peak period travel from those households. So in those peak period is when the benefit of express lane is the highest. And in some ways, if you look at the data from that setting, the travelers can benefit more. Is it still working? Can you still hear me?
Yes, you're good.
Okay, I'm really sorry, but I don't know what's happening. Okay. Okay, so but even with that issue in place, there are concerns around the issues that express lanes can pose. For example, we often see that like if there are tolls which are very high, like people like news articles tend to pick those up very quickly. And especially in North Carolina, there has been a little bit resistance against some of the express lanes that are being deployed in Charlotte, even though there has been somewhat better understanding, that I-77 express lanes are functional, but there is in general resistance against these tolls. So if you if we specifically look at some of the emerging price managed lanes, they pose us several complexities if we try to analyze equity issues. For example, many of the express lane facilities have these complex entrance and exit structures where travelers can enter at different locations and exit at different points. Similarly, there is many of the cities across the United States are considering networks of express lanes, where it's just not one corridor, but across multiple corridors where different types of express lanes exist, and in some ways they are coordinated. At least the vision is to have them coordinated so that travelers can benefit all across the region. So because of this complex structure, which is spanning like large area in geography, as well as having complex structure to access these lanes, there is complexity in analyzing these express lanes, and especially from an equity perspective. So the specific questions that we want to have is like, how can we sort of quantify and address some of the long-term equity impacts of express lanes? And here I want to bring two perspectives. So one is a long-term land use or planning perspective. So here is where we consider looking into the future, what will the traveler behavior be given certain changes in like projected future traffic demand, etc. So here again, we may consider evaluate options of, if not managed lane, what other choice would have been in place, and would that have been more beneficial to travelers? And would tolling partial lanes be better than tolling all lanes? So those factors play in planning perspective. And from pricing and operations perspective, we argue that here is where we look at exact, like how is the toll charged on day-to-day basis, and is that more equitable or not? So for our focus was a little bit more on the design of tolls per se, like how can we choose to design tolls such that they are more equitable, and looking it through the lens of resource allocation, where the resource that we are allocating is like access to low travel time on the corridors. Okay, so here is where the modeling approach part is critical. So given that our question is, how can we quantify the benefit and cost differentials across population groups, and can we design tolls to address that differential? The question, the typical standard that is followed, which is kind of laid out as this 5-step procedure as part of the NCHRP report, is that anytime you want to address equity issue in any project, you want to start with identifying population for analysis, like who is in need for, like who all are involved, identify the needs and concerns of those population, identify the impacts of the proposed projects, then determine a few disparities that can exist. For example, are some people benefiting more than the other, and then develop strategies to mitigate them. And when we look at this 5-step procedure, these last 3 steps in particular kind of rely very heavily on sort of measuring what would be the impact of proposed project. And in some ways, these steps require careful design of models that we use to understand transportation systems, especially for equitable objectives. So in some ways, like that's the focus of our work, is looking at modeling approaches for addressing equity. Here we look at different scale of models, planning models, as well as operation models, and identifying how can we measure equity and address disparities that can exist. So as I said earlier, like some of the work that I'm presenting is still in progress, so I may not end up having a very concrete recommendation to you, but I will be very happy to have thoughts and discussions on like some of the ways we can sort of take away the findings from these models. So what I'll present over the next sort of 2 chunks is like some of the details of the planning models and the operation models, and looking at how can we incorporate equity considerations as part of it. Okay, so whenever we sort of think about long-term planning, there is a broad categorization laid out in Transportation Planning Handbook. So we start with establishing goals of the community for which we are doing the planning, sort of doing existing inventory, analyzing that inventory, doing a forecast of land use, using that forecast to predict the future trips, how many trips will be distributed across different modes, what routes will be chosen, and then making a recommendation on which plan is better or not. And the modeling focus of our research in some ways aligns with these steps, where we are predicting how many people will end up using the express lane facilities and not use them. So if we look at whenever we talk about long-term transportation planning, there are 3 component models that are involved. So first model that we commonly incorporate is a single agent decision model. Here we kind of model the behavior of single individual who is using the transportation system. So this can be done through modeling their choices that they are making on a day-to-day basis, for like, for example, mode choice, route choice, etc. So it's a single agent decision model. That's one component. The second component is the congestion model, which sort of incorporates interaction among multiple agents. So if everybody, for example, were to choose one route, that route will become congested. So sort of capturing that interaction is done through this congestion model. And if the structure of the problem permits, we typically are interested in looking at like equilibrium, steady state of this system, where what is the state where the choices of travelers are in steady state and no one has an incentive to switch their choices given the choices of others. So once we have a sort of a baseline equilibrium model, we look at models for transportation policies that achieve certain objectives. So this is where we evaluate different transportation policies and see how well will they do if given that this is how we are characterizing the behavior of travelers. So for example, if we have an objective of say minimizing delay for everyone, that if we use this kind of framework for modeling it, like we might have a guidance on which policies we can incorporate and what will be the benefit of different policies. So this is like a broad general framework. So the thing that kind of changes for express lane facilities is that there is a real-time information component that impacts the decisions of travelers. And that's something that has not been carefully addressed in the literature. So for example, whenever you're using express lane facilities, there is real-time information on the tolls, the travel times, as well as some of the the toll travel time, and like you get information on like how much will you benefit from using certain, entering at certain location. So this real-time information impacts the way people make decisions on those express lanes. And additionally, the thing that is different for, especially when we look at equity objectives, is there may be conflict among different objectives that are in place. Okay, Just checking the time. So with that, so what I want to discuss is how do we address some of these two issues as part of our like standard planning model analysis. So firstly, I'll focus on the real-time information. How is that integrated as part of the equilibrium model? I might skip a few details, but I think I'll highlight the key points in respect of broader understanding. So one part with express lanes, like let's say if we approximate the express lane facilities like a directed network, where there are nodes where travelers can make decisions on whether they want to continue on managed lane or take general purpose lane, for example. If we create a directed acyclic graph, we can model the behavior under the presence of real-time information using the methods for online shortest path. So the idea of behind online shortest path is like, given you are at any node, say node 1, and you just received information about what would be the travel time states or toll states on different links which are downstream, which route should you take if you want to minimize your expected costs. So the goal of online shortest path is to minimize these expected cost to destination. And broadly, they have been studied very well in the literature, and they are broadly categorized around how much information is an individual accessing. Is it full information, no information, or partial information? And we also look at the stochasticity, whether it's full dependency or partial dependency of link travel times. So again, choosing different combination of information access and stochasticity allows for different flavor of models, which some of them may become very tractable and analytically neat, whereas some might become like a little complex, but more realistic. So I guess there is a trade-off there as well. But so in my research, in some parts where I focus on certain assumptions so that the model is still tractable in the end, but that's always the flaw with models. Like all models in some ways are wrong, but they can be useful, hopefully, with proper calibration and application. Anyways, so that's the part with fixing the single agent decision model. So once we now have a model where we know how each individual traveler is moving, now we want to characterize the congestion model, like how the interaction will be captured. So that we do through specification of supply side uncertainty. So here I'm categorizing the travel time. So we state that each link in the network can exist in different states with different probabilities, which we assume we know beforehand through prior survey data or prior analysis. So for example, this general purpose lane can exist in 2 states. The first state has a travel time where it increases at, the travel time on the link increases 5 times the number of vehicles using the link. So it's a simplified link performance function with probability 0.6. And the second state is the travel time increases twice the rate of number of vehicles using that link with probability 0.4. And similarly, we can define different toll states on these links which belong to express lanes. So where the toll tau can be different for different states with different probabilities. So in some ways, we are sort of characterizing the uncertainty that can exist on these express lanes through the static probability distributions, which we assume we have access to through prior data. We might question, like, is this reasonable, whether we always have access to it or not? The answer that the answer is like, yes, we can derive probability distributions from it. The question of feasibility of doing it for any kind of general express lane, like, and that amount of data needed to build more confidence in these states and probabilities, that's a question for debate, I guess, or not more than debate, it's like future research. Okay, so that's supply side uncertainty. We define links in different link states. And then we have other characteristics, like there is a network, there are some set of zones where people begin their trips and end their trips, and there is a demand between each zone, and there is interaction between the agents modeled through these cost functions, which are which we assume is a separable function of the link state flows. And then now we model the information provision, like how is information given to travelers. So when a traveler arrives at a node, they receive information on the links which are just immediately downstream. So this is another assumption we make, is like for tractability, that we assume that when we arrive at node 1, you only know information about link 1, 2, and 1, 3, because they're immediately downstream. So in some ways, we can characterize this information through this information vector, which is a cross of the number of states of all the downstream links from that node. So then we define a node state is like the potential information states we can reach when I arrive at node 1 as it's like a decision point in the network. So for example, if I arrive at node 1 and I see that the toll is say 25 cents and the travel time is 5x, so that's one node state. And if I arrive at node 1 and I see that the travel time is 2x and toll is 25 cents, then that's second information state. So, sorry, second node state. And in some ways, we want to model like what will the traveler do if they arrive at a node in different node states. So that's the philosophy. And we captured this through the concept of routing policies, where a policy, like the policy that a traveler is following as they are moving from one place to the other, is that tells them what action to take in each node state. So for example, this this policy here is telling me that when I arrive at node 1, and regardless of the information I receive, I always take the top link. Similarly, this policy is telling me that when I arrive at node 1, regardless of the information states, I go on the bottom link. A policy, this one, would tell me that if I arrive at node 1 and I see the link is travel time is 5x, I go on the top link. If I arrive on the node and I see the travel time is 2x, I go on the bottom link. So in some ways, like this policy maps the node state to the next node that I will take. And we can solve this shortest expected cost policy to model that every traveler is trying to go on the shortest possible path by solving them and formulating them as a Markov decision process. Okay, so that's the modeling of information. The final component is the model of cost functions. So here again, I'm skipping a little bit of details, but the idea is we capture how much expected cost will be incurred from any given node if I follow policy pi by this variable ci pi. And then we can relate the costs on each link with the costs from each node through a q pi matrix, which is defined as a matrix from each node to each link state. And similarly, we can quantify the policy flow and as a function of the link state flow in a similar manner. So once we have that, the framework, we can define the principle of equilibrium for the case. And again, this principle has been established in the literature, so I'm not saying this is my unique contribution, but the value that I'm bringing is the multi-class nature, which will enable us to look at travelers which are from different classes. So backtracking, so this principle of equilibrium states that the equilibrium behavior among different travelers would be the one where all the used policies have equal and minimal expected cost. So if a policy has more than 0 people using it, then the cost of that policy should be the minimum across all policies that can exist. So we can show that if the cost functions are strictly increasing and positive, then we can formulate the problem of solving this equilibrium as a convex program. So this is pretty standard, even within like a traffic assignment literature where we don't have the real-time information component. And even if we incorporate multi-class groups of travelers, we still can argue that the cost functions are convex. So because of the convexity of the problem, we can solve it efficiently using like algorithms such as gradient descent, etc. So without going again into much detail, we solve these through using gradient projection algorithms, where the idea is we start with like a shortest policy. We load all travelers on it. Then the goal is to shift travelers from a non-shortest path policy to the shortest path policy, such that like in the end, the expected costs are equal among all the used ones. And the convergence criteria of this is the relative gap metric that is commonly used again. So what we did was we have formulated the multi-class user equilibrium with recourse problem. So here we have different groups of travelers who value the time differently. So maybe I should have emphasized this earlier, that the multi-class nature of this problem is that there are different groups of travelers, and they have like some travelers may have low value of time. So let's say $10 an hour, whereas the others have higher value of time. It's typically seen that the value of time correlates with the urgency, with the income of the traveler. So in some ways, like typically we see that high income travelers have higher value of time, whereas low income travelers have low value of time. And so in some ways, by making this problem multi-class, we will be able to see the split of how much benefit is one traveler getting for the other. So far we have looked at one network here, which is the North Tarrant Expressway subnetwork in Dallas. And if we compare the gradient projection algorithm performance against the Frank-Wolf-based algorithm proposed in Rambha et al., it converges faster to and produces solutions with lower relative gap sooner. Okay. So the key thing that we have found is if we continue to use traditional user equilibrium models. So remember, the traditional user equilibrium models will not incorporate the adaptation to real-time information. So if we continue to ignore them, then we are underestimating we can potentially underestimate the flow on express lanes by up to 45%. So this is again a result from the simplified subnetwork analysis that we have done on the North Tarrant Expressway. So now if we come to the equity consideration, so this is where some of my current work is looking at. So the broad idea is we want to design tolls. So now that we have seen the equilibrium characteristic of how single agents interact with others, an equilibrium model for the scene, now our goal is to design a policy model such that we can create more equitable solutions. So we are trying to solve this through by formulating it as a mathematical program with equilibrium constraint. So the sub problem here is the interaction problem, where we solve the equilibrium, the multi-class user equilibrium recourse. The main problem, which is the policy problem, is to minimize the differentials of the delay. So here I'm saying that choose a toll policy such that the maximum, the travel group which suffers the highest delay, if I subtract the difference with the traveler group which suffers the lowest delay, I want to choose a policy that minimizes that gap. So in some ways, we want to sort of reduce the excessive benefit that one group might have over the other. So we are currently working on scalable heuristics because this problem is very, because of this MPEG nature and non-convexity, it's hard to solve it exactly. And we are currently looking at, the research on network design literature has considered several heuristics to address this, but our goal is to sort of translate those to this user equilibrium with recourse concept such that it's more scalable and it can be done efficiently for larger networks. Okay, so that was the sort of our analysis for some of the planning literature. And again, the big takeaway that I want you to have is that accounting for sort of adaptation of travelers to real-time information is critical when we analyze long-term planning effects of managed lanes. And that effect can then impact our equity analysis in the end. So now let me talk about equity considerations and models for dynamic pricing. This is more of an operational scale, like a day-to-day scale model, instead of looking into the future. So here again, I have an express lane facility where travelers can make decisions on which lane to take at what time. And there are different locations where the sensors are placed, and we are making toll decisions based on those sensor readings. And there are some links which charge the toll, so where the toll gantry is located. So when we look at dynamic tolling models, we can broadly categorize the components for models as two of them. So one is the demand model, which kind of captures the effect of how travelers, how would we know how many travelers are choosing what link at what time? So in this, the demand model effectively captures the choices of each individual, like similar to the single agent model in the planning step. So whether to travel or not, departure time, lane choice, etc. And we also consider different factors that can influence those choices, like toll and travel time, which are alternative specific, and a little bit more individual specific, such as income, which is approximated, again, proxied through this variable called value of time. And then we have the supply model, which sort of captures the interaction of demand with infrastructure. And I mean, I'm calling it supply model, which is maybe a fancy term, but the idea is like simulating the traffic. So it's like a traffic flow model for which incorporates the queue spillback and like moves people from one location to the other in some ways and predicts the traffic flow at each link and point in time. So given the two demand and supply models, we have a toll optimization model, which tries to determine what toll to charge at what time of day, given the constraints on maximum and minimum tolls, and with a certain objective in place, such as either a system optimal objective or a revenue maximization objective. Okay, so if you look at the current literature on models for express lanes, there have been several methods to solve this program for what toll to charge at what time of day. Like people have used dynamic programming, feedback integral control, model predictive control, and deep reinforcement learning. And in effect, like some of these models like all have disadvantages and advantages for each of them. And in the end, they are at least better than doing a very simple like a up-down type of tolling. Like, for example, if you just do a very simple tolling of increase the toll if there is more people on general purpose lane, decrease the toll if it's less people. So I feel like that's these kind of models do better than better in terms of achieving a certain objective. The objective can be revenue maximization, it can be minimizing delay, etc. So the focus that I'm trying to bring in is like having the explicit objective of addressing equity as part of these. So if you look at some of the recent literature, especially this work by Dr. Hall, and it has looked at the Pareto efficiency of tolling for express lanes. And it has been shown that there are toll policies such that no traveler is worse off. So especially when we talk about the equity perspective, that if we toll a portion of lanes even before spending the revenue to the public, no traveler is worse off by suitably pricing only a portion of the lanes. And travelers with higher value of time and higher flexibility, they are the one who benefit the most. So if you look at like the distribution of travelers, which is now in terms of how much do they value their time and how much flexible they are in terms of their travel schedule, we see that the blue area is the one where travelers are benefiting the most. So if we price all the lanes, then there are some groups which do not benefit. They end up sort of doing worse when there was no toll at all. But if we only price a portion of the lanes, everybody is at least not worse off than before. But even this analysis is like good from economic standpoint, but it also sometimes raises concern, like, is this justified? I mean, there are still some groups of travelers who are like benefiting and some groups who are just not benefiting at all. So I mean, there is, if you look at the debate in the social justice and equity literature, there is not clear consensus on what is the most equitable option. But broadly, if you just define equity as the one that minimizes the differentials across group, even this is not very equitable because we want to sort of have more uniformity. But the question then becomes, can we even achieve that just directly by pricing half of the lanes? So the thing that we are investigating is, can we do it by having differential prices in the first place? So for example, if we charge certain groups of travelers different rates, then is it possible for us to have a more equitable distribution of delay or welfare change, for example? And also, like the model was done for single entrance and exit express lane, and with the optimization objective of minimizing the costs, which may or may not hold true for very complex express lanes. And especially in some of my past work, I've shown that like if your objective is just to maximize the revenue, then in some ways there is like this evil policy that you can have. In some ways it's an unintended consequence, but it's a pure consequence of maximizing revenue. And the unintended consequence is that like to make more revenue, you intentionally jam the regular lanes so that they become more congested, and then you can harvest more revenue later. So in some ways, like when you are maximizing revenue, you create more jam on regular lanes and you generate much higher revenue. And whereas if you're just minimizing delay, then your toll policy can be a little different. The revenue will be lower, but also the delay will be lower. So what we were trying to look at is, can we quantify these unintended consequences and measure these differential impacts? And specifically, if I kind of go back to the 5-step layout of the NCHRP report recommendations, in some ways we are categorizing the population along the different values of time. We are identifying that their needs and concerns are that they want to desire to have a low travel time. We are measuring the impacts using an mesoscopic traffic simulation model. We are saying that disparities among the group is the differential of delays. Like if some group is having much lower delay than the other, that's a disparity. And our goal to address it is through design of toll discounts, subscription coupons, or differential prices. So again, if I'm laying out my assumptions for equitable toll analysis, because there might be debate on whether even this process is really addressing the equity issue in first place, because sometimes people may not even have been able to afford a car to use the managed lane in the first place. So this framework is not capturing it, because in my population, and I'm not distinguishing between travelers who are captive riders who have to use transit. So, I mean, that's the limitation, because like equity in itself is a very broad concept. But if we make this assumption, we can continue to use the framework that I've established so far. And I'm hoping, that's my long-term vision of my research, is to have a more holistic equity analysis models. That way, we can address different components more clearly. And for simplicity of analysis, I'm also assuming that the demands of travelers are inelastic. So for example, if I charge a very high toll, like people won't stop traveling or people won't switch to another route. This may be a drastic assumption, because people do switch away from managed lane if there's too much toll. But for simplicity of analysis, we continue to make this assumption. So our test networks include the express lanes on Mopac Austin. It's a loop 1 13-mile highway in Austin, and some abstract networks which are sort of simplified from the real world implementation. So many express lanes have this single entrance, single exit behavior, so SESE. Some have double entrance, single exit, and some have this. So this is based on the LBJ corridor in Dallas, etc. We assume that there is a discrete value of time distribution, that the travelers in our population are distributed along these 5 groups with different proportions. And we have certain limits on the maximum toll, minimum toll, etc. And the way we do kind of simulation analysis is we have a multi-class cell transmission model for the simulation of traffic. We govern the lane choice of travelers using 2 types of models. One is a logic model. It does a probabilistic allocation of travelers. And one is a decision route model, which is more deterministic, but involves a little finer comparison of which routes to compare. We simulate toll profiles over 5-minute intervals. So one of the key concept that you might think from this is, anytime the demand for people who are using express lane is higher than the capacity, there will be inevitable congestion. However, we can show that different toll choices can still underutilize the capacity of the corridor and result in this additional congestion. So of course, there is some congestion which is inevitable because there are more people using the express lane. But just by the choice of toll, we can actually create more congestion. So our goal is to sort of address this issue where we continue to improve the utilization of corridor capacity. So if you remember the earlier discussion, I was saying about how different tolls do differently on the different objective frontier. So here I'm plotting each blue dot is a toll profile. On the x-axis is the revenue that it generates, and the y-axis is the total system travel time, or the delay that it generates. So as we see that higher revenue profiles end up creating much higher delay for everyone, because of this jam and harvest nature, which I explained, where if you're just maximizing revenue, then you will create additional burden on people. So effectively, we typically, whenever we do multi-objective analysis, we look at the Pareto frontier, which is like the non-dominated solutions among all the solutions that can exist across these multiple objectives. And when we look at this Pareto frontier here, there is additional congestion burden that falls on travelers with lower value of time. So if you just look at the Pareto frontier and we split the delay across travelers with different value of time groups, we see that there are certain groups of travelers which have much higher delay than other groups of travelers. And this gap sort of widens the more is the revenue of the profile. So in some ways, if we are approximating this value of time as a proxy for income, this is what I'm quantifying as a delay differential, is the absolute range of average delay per vehicle for all travelers across that different groups that I have, like different value of time groups. So that's the equity metric for our analysis. And what we have done is we have analyzed what factors impact this equity differential. So we have found that if the demand diversion is ignored, if we don't consider that demand is diverting to other routes, then the delay differentials are higher for higher demand. There is an increase of up to 6 minutes when the demand is at the base level. Similarly, if we incorporate demand diversion, and again, this was modeled by assuming a certain characteristic of the alternate routes, so I'm skipping that detail. But if the demand is diverted due to presence of alternate routes, the reduction is lower. So that's like good news, that if there are alternate routes, then higher demand would not create too much of equity differential across the group. But if there is just one route that connects one region to the other, then people are more logged into it. And that's when the equity differential will be significant if there is more demand. Similarly, if we increase the toll upper cap, the delay differential tends to increase up to 16% increase when we increase the tolls from $4 to $8. And finally, if we sort of adapt our lane choice model and we consider that people are not always rationally behaving and not choosing the shortest possible option, then and that they behave more stochastically, then also the delay differentials are lower. So again, the choice of which model is more accurate depends on the data that we collect through the facility. Of course, like humans typically are more stochastic in nature, but if we are looking into the future when there are more connected and autonomous cars, they will be making more like a more proactive, rational decision, should I say. And in that case, if the delay differential will be higher across the groups. So in some ways, like I want to sort of wrap up like some of the findings that we have had so far. I know like, at the present, we are currently looking at like to bridge this differential, we have looked at the charging different groups of travel at different discounts. So we are currently optimizing what % of discount to offer each group. And I'm sorry, I don't have like as much positive results to show so far, but at the same time, our intention is if we charge certain groups of travelers with say X% discount, we will be able to create more equitable distribution, and we can utilize the underutilized capacity of the managed lane much better. So our so far findings indicate that we should be careful in integrating the travelers adapt to real-time information if we want more realistic prediction for long term. Similarly, the choice of dynamic tolls do impact the delay differentials, where higher tolls and higher demands worsen the differentials. And if we allow demand diversion and alternate choices, that can lower it. And finally, if the capacity is fully utilized, the delay differentials are lower. So remember like the idea that there is some tolls which can underutilize the capacity on managed lane. So we probably don't want them because they tend to create higher differentials. Even though, so this may sound very intuitive, but like people might be like, duh, we probably know this. But at the same time, like the powerful reason, purpose of our research is having a good methodological tool, so that way we can validate some of these results. And now our goal is to design tools such that we can show that these delay differentials are reducing by having those discounts. And I think we have an experimental setup already. It's just like I couldn't have the results so far, but feel free to reach out to me if you're interested in knowing more about some of our current results. So as I mentioned, we are currently working on the long-term planning perspective, where we are looking at how to solve equitable toll design for the planning perspective by having efficient methods for MPEG solutions, MPEG problem. And again, identifying what policy guidance to give. Because in the end, it's the policy guidance that matters, like whether or not to give discount to everyone, whether or not to give 3 free trips versus 5 free trips. Like those kind of policies are something that we want to evaluate. And like from dynamic pricing perspective, our model has a little bit of limitations in terms of the departure time choice. So that's the inelasticity that I mentioned. So we hope to sort of incorporate that and finish the optimization of differential tolls. And finally, our intention is also to extend these results to some real world implementation. So hopefully, if any agency would be interested in trying out some of these methods or experimenting. And I know that some of the agencies are already doing that. For example, in LA and Virginia, like they have some certain discounts for certain groups of travelers, but they are being rolled out on a very like trial basis. And this is a very active area of research. So, so at the same time, like it will be exciting to see if we can have some of these real world implementations and like see them in practice. With that, I'll stop my discussion. Thank you so much for all your attention throughout, and I'll be happy to take questions now.
Thank you so much, Dr. Pandey. I will open the floor up for any questions. I think we have time to take a couple. Any from the audience?
I have a question, and this may be common knowledge because I'm not a researcher, but how are these things determined now? How do they, like for instance, how did the toll get to be $47 in Virginia? Or how did they determine gem and harvest times now if they don't use research?
Yeah, that's a good question. I would say that it's not that they don't use research. I think they're relying on some simplified heuristics, which are more intuitive in some ways. That I think the heuristics are like you should increase the toll when there is more travelers using the general purpose lane, because you want to keep the managed lane congestion free. So there are some simplified heuristics, which in some ways, like there's nothing wrong with those heuristics. Like they align with our intuition, they help the agencies make decisions well, which is good. It's just that they may or may not serve the purpose very well. So I think lately there is more research on data-driven models for optimizing tolls. So you observe the speed profiles, delay, sensor profiles on, and then decide what toll to charge. So, and I think that $47 toll that I mentioned, I think there was a lot of discussion around it. And I think people are putting price caps on maximum tolls, and that hopefully will be beneficial. But that was a one-off case, and that's why the media picked it up.
Is that 47 toll road around DC?
Yes, in Virginia. I think
I thought it had to be, because who else would pay that?
No, good question.
All right, good question. Any other questions from the audience? No, I have one, and it's just a clarification question. So in terms of the grouping that you actually investigated, were those groups primarily just based upon their value of time?
The answer, yes.
Okay.
We considered the groups to be along the value of time.
And that was directly or positively correlated based upon research with their income.
Yeah.
So the reason for the greater, I guess, disadvantage of these tolls is that they're not necessarily willing or able to pay the increased tolls. Is that pretty much the rationale there? Okay. Okay.
Yeah. So in some ways, because like their willingness to pay is lower because they are poor. Sorry,
that's okay.
Low income.
Okay.
And that's why we want to quantify that. I mean, of course, like there is another dimension that can be incorporated, and some researchers have done it. The one that I mentioned, like looking at the flexibility of travelers, not just looking at their value of time, but how flexible they are. Yeah. But it's slightly tricky to capture those departure time choice models. And I guess that's our next step, hopefully. But
so how would these discounts be operationalized? So, I mean, because I'm just considering what my experience has been on toll roads, where of course it's not until you actually get on the toll road that you're charged. So how is it, how do they differentiate this group from another group when it's your discretion whether or not you actually get on the toll road?
Yeah, no, that's a good question. I think like how to implement this in practice. Yeah. And it is a challenging thing to do because there is always, I think it aligns with any kind of economic type of policy. If you are benefiting some group, giving some group more than the other, there is always a question of how do you implement it. And I feel like to answer your question, the way sometimes they do it is like your toll tag reading is commonly associated with your account, right? So in some ways, if they kind of identify that you classify as low income traveler, then your barcode can sort of charge a lower toll when you kind of pass through the express lane instead of the higher toll. Or
so they would need
discount.
to create. So they would need to create like a profile or something, and that profile will include income information that would, I'm assuming, would have to be validated in some way or another.
Yeah, I think there is a lot of gap. I think I agree that to make it practical, because there can be debate on people like falsely claiming whether they are they qualify for it or not. So it's a tricky area to, even if you're giving discount, like making sure it's fairly done. That's a very tricky thing to do. But I know that LA has done it, and the way they have done it is they give a fixed credit to, like, say $50 virtual credit that you can use for. Okay, I may be very wrong in terms of is it yearly or monthly, but yeah, it's like some sort of a fixed credit. Yeah.
Okay, excellent. Any other questions from the audience? All right, well, I'm gonna take that to mean that your research was very clear to them and they understood and had no additional questions. But as you can see, Dr. Pandey has his email address up on the slide. So please feel free to reach out to him directly if you do have some additional questions. This is ongoing research, so this project is not complete. So I'm sure he welcomes and it is open to feedback from others as well, especially if there are some additional factors that he might want to take into consideration.